lectures where we'll really be sort of introducing new concepts. After that, it'll be sort of like exploring, using the concepts we've already discovered and exploring fields that are kind of maybe closer to home for you guys. Okay, so it's 5 past. I think we can start in earnest. So let's go. So today we're going to be studying chaos in a particular type of system, so in what are known as dissipative systems, and we'll have a look at what happens, at strange attractors. So these figures, you've already seen them, and I've kind of loosely introduced them to you, but we'll have a more detailed look at what they actually mean, right? And we'll also have a look at something that's quite an interesting feature of chaos, right? Is its relationship to fractals. So this is a fractal, right? This is a Romanesco cabbage or broccoli. So fractals are things that have what's known as self-similarity. We'll get back to that later. Okay. So first of all, quick recap of yesterday's lecture. We saw a possible route to chaos, right? How a system goes from being periodic, well-behaved, to becoming chaotic, right? We saw that, as you increased certain parameter values, fixed points of the system were destabilized, and it was these bifurcations, right? The fact that these fixed points are no longer stable, that meant that the system was driven on the route to chaos. One of the interesting things about these bifurcations is that they're universal, in the sense that what we looked at, we looked at a few different dynamical systems. We looked at the Duffing oscillator, we looked at the Lorentz map, at the Lorentz system, and we also looked at the logistic map. All these systems, which are drawn from very different fields, actually display the same kind of behavior, right? So this tells you something interesting. It tells you that the underlying dynamics don't really matter as long as they're, chaotic and non-linear, deterministic, and sensitive to initial conditions, because all of them will behave in the same way. We even saw that there was a number associated to that, which I'll come back today because I think we introduced it rather briefly yesterday. So there was even a number associated with all of these different systems, right, which was the ratio of the distance between successive bifurcations, which is known as the Feigenbaum number, which is an interesting thing to see, right, that the same number would crop up in systems as different as, a weather forecasting model and, a simple demographic model or, a driven oscillator. We also briefly touched upon kind of one of the deep roots for the transition to chaos, which is the notion of scaling, right? So what we saw is that basically chaos occurs when small changes become large. And we saw that there was a parallel with certain types of phase transitions, right? So changes in the states of matter, where it was the same kind of broad idea, right? Something happening on very small scales that suddenly starts having very dramatic effects on the larger scales, right? So microscopic, macroscopic. We applied this insight as well to the realm of turbulence, which is an old-standing problem in physics, right? And saw that there was a kind of similar idea, right, of a stable flow being destabilized as small fluctuations get amplified until you go from a nice laminar flow to turbulent flow. So this will go back. This I want to sort of refresh your memories about. So this was the logistic map and how the fixed points change as you increase parameter value, right? So if there's one thing you can take away from this whole lecture course, right, this image here is sort of the thing, well, that and the strange attractor will be the two things we'll be coming back most. So as we recall, what was happening is that this line describes the fixed point of the system. So this is the steady state that is reached by the population of rabbits in the logistic map. So if you have a small starvation rate, then that thing is just constant, so the population settles to one value. Then you had a first bifurcation, where suddenly the population started to oscillate between these two values, and we saw that there was an unstable branch here. And then this bifurcation happens again and again and again on smaller and smaller scales. And the interesting thing was that for very different, so this is for the logistic map specifically, but actually for any kind of map of this broad family, you always had a ratio, with the ratio of the distances between the successive bifurcations. So for instance, L3 divided by L2, L2 divided by L1, L1 divided by L0. These ratios are actually equal to a constant. And this constant doesn't change depending on the function you're looking at. So it works for the logistic map. It works for maps based on sine functions. So this is what's known as the Feigenbaum number, and that was a display of universality, right? So this image is interesting because it shows you both universality. It also also shows you that fundamentally chaos has something to do with branching behavior on repeatedly smaller and smaller scales. It also kind of told you something intriguing, which is that a chaotic system is never fully chaotic everywhere in its parameter space. Basically, you will always find this structure of alternating between chaotic regions and nice, well-behaved periodic regions, right? And if you were to zoom in on any one of these regions, you'd find the same behavior, right? So certain patches where everything is chaotic, interspersed with patches where the system behaves nicely and periodically. And this is, again, you will see this kind of starts to look fractal. Okay. So today what we'll be doing is, first of all, I'm going to reintroduce chaos from a slightly different perspective, right? So far I've introduced chaos as a property of dynamical systems, displaying sensitive dependence to initial conditions, nonlinearity, and determinism. But today I'm going to introduce it as a question of scale, meaning we're going to look at it more physically, sort of like what is it that manifests itself in chaotic systems, right? And we'll rework a little bit this analogy with phase transitions, because I think I went over it very quickly yesterday, and I got the feeling that it wasn't, I don't think I was as clear as I could have been. So basically we'll look at chaos from this angle, how things on small scales start to manifest in the behavior of the large scale of the system. In order to do that, we'll also have a brief recap of the things we've seen so far. So I'll reintroduce some of the vocabulary. So what's a dissipative system? What are phase space portraits and how systems evolve in this phase space? We'll have a second look at sensitive dependence, this time from the point of view of the stuff we saw yesterday in terms of destabilized fixed points. And nonlinearity, and we'll introduce a new term also, which is recurrence, the idea that actually a chaotic system is bounded, right? It never quite repeats its behavior, but you saw, it kind of stays in a broad region in the phase space. So this will basically motivate the appearance of strange attractors in phase space. They were these sort of like swirly patterns over which a system evolved, which never quite seemed to repeat themselves, but where you had basins around which the system stuck around, but never quite going into periodic motion. And this, basically, when we look at the structure of strange attractors, we'll see that they display the broad properties of what are known as fractals. So basically fractals are a way to, for instance, fit an infinite area into a finite volume, right? We'll talk a little bit about the implications of that for, for biological systems, or even a little bit in finance. Actually, I found a short paper on that recently. Okay. And eventually, we'll relink all these fractal things to the study of chaotic systems. Okay, so this is this main important question, right? So the question of scale. Basically, in physics, you have two broad ways of seeing things. Either you're looking at a very simple system, so for instance, two molecules interacting, two particles, two planets interacting. So in these models, we know how to model the behavior exactly. It's not chaotic, it's all linear and well-behaved. So we can see exactly what happens in the individual interactions between subparts of the system. But obviously, as the number of subparts increases, we're no longer going to be looking at the detailed interactions between two molecules. For instance, if I were to describe the air in this room, I wouldn't bother describing the motion of every single molecule in the room. What I'd do is I'd just give you the temperature and the pressure, right? And these basically are enough to draw all the information contained in the system, right? You don't need me to tell you anything more than the temperature in this room is, 25 degrees, and the pressure is one atmosphere. The reason for that is that when you average this kind of, if you zoomed in and looked at all the molecules in the air, you'd find very, stochastic random motion going on everywhere. But ultimately, that's not of interest, right? Because when you zoom out, the only thing that interests you are average properties of the system. And for instance, temperature will basically be linked to the average velocity at which the molecules move around. Pressure will be linked to the average momentum that these particles have. So you have two extremes in physics, right? On the one hand, detailed understanding of how two-body interactions work, detailed understanding of how things operate on very small scale with very small systems. And then you have a very good understanding of what happens when you have a system of billions of molecules or of subcomponents, because in that case, the only thing that interests us are average properties. But basically, we know that there are phenomena which kind of fall in between, right? Which require both knowledge of what happens at the large scale and knowledge of what happens at the small scale. And we already saw two of these examples, right? We saw turbulence and we saw phase transitions. Because ultimately, what's turbulence? Turbulence is suddenly, you start having this nice, smooth flow, and suddenly it becomes very susceptible to noise, right? But where's that noise coming from, right? What's the thing that disrupts our nice laminar flow? Well, it's just the motion of molecules, basically. So suddenly the very small random behavior of things at small scales gets amplified and turns into these kind of observable macroscopic phenomena like the swirls and turbulence. In phase transitions, you have something similar, right? Because what happens in a phase transition, for instance, if you're cooling down water vapor until suddenly it turns into liquid water, well, basically, in the state of a gas, the only thing that interests you is the average speed of the molecules, right? In the gas state, you can treat every water molecule as kind of a little billiard ball bouncing around against other billiard balls, and that's a very simple model which allows you to explain the properties of a gas. But at some point, once you've cooled down the system, you start having to notice the effects of the interactions, the more complicated interactions between neighboring molecules, which is basically the reason that, that a liquid has fundamentally different properties to a gas, right? A liquid fits into an open container, a gas will just occupy all available space, right? And this has something to do with the microscopic interactions between the molecules of water, for instance. So a phase transition, kind of like turbulence, is the manifestation of some dynamic that occurs at the microscopic scale, manifesting itself at the larger scales, right? So, quickly, having a look again at turbulence, right? So this was the standard example of, for instance, some cigarette smoke going up, accelerating gradually, and going from a nice smooth laminar flow to turbulent flow, right? And what we saw is that, for instance, you could model the speed, the speed of the layers of fluid as something which goes like that. So this is laminar flow, right? That's the speed. These arrows represent the speed of the fluid layers. And they have this broad structure, right, of being small at the edges, increasing over the center, and re-diminishing as you go to the other edge. So essentially, this kind of flow, it's completely stable, right? There's nothing particularly complicated about it. If I were to increase the velocity here, so for instance, if I decrease the friction with the walls, then basically I'll just have the same thing, but slightly larger. So here the fluid's accelerated, but fundamentally, the structure is conserved, right? As speed increases, we're still seeing the same structure of the flow. But eventually, so this is the bit here, right? For a while, we maintain the laminar flow, just the speed increases here. This is linear, right? This is linear evolution. But what starts happening once you reach a certain critical point is that actually the difference in speed between neighboring layers becomes so large that actually a tiny fluctuation here, so one little molecule just deviating a little bit from this trajectory. So for instance, when you model a flow, you're really only looking at layers of fluid, but these layers of fluid, they contain billions and billions of molecules, right? So you can imagine that there's some random movement within the layer of fluid due to the motion of the molecules themselves. So imagine in this layer, one little molecule just bumps into another, and it sends a patch of the layer upwards like this. But now this patch here is sent into a region of much slower flow, right? So as your molecule exits here, it's being slowed down, and it'll start doing little swirls, right? So at some point, instead of having neat laminar flow, we're going to start seeing these swirls which mark the transition to turbulent behavior, right? And you can see that what triggers the appearance of these swirls is just tiny, tiny fluctuations, microscopic fluctuations in the flow that disrupt the entire structure of the flow because the system is unstable. And so you remember, instability means that a small perturbation will just grow and grow and grow. And the point is they won't grow infinitely because you've still got a finite system, but it'll grow until the behavior is markedly nonlinear. So that's a kind of very sort of hands-on view of how turbulence emerges. Essentially, laminar flow turns turbulent because tiny, tiny microscopic fluctuations get amplified by instability in the system until you reach full turbulence. So the other system that we saw yesterday, which also manifested the same property, right, of having small-scale changes entailing dramatic consequences on the large scales, was what's known as a phase transition. And we looked at one particular phase transition, so I don't know if you remember, there was a little video. Essentially, you take a magnet, you heat it, it loses all its magnetic properties, and then as it cools back down, suddenly the magnet reacquires its magnetic properties. And I had a brief, I showed you very briefly a kind of microscopic model for how this works. But I think I want to sort of like rework this, but with a finer understanding of that idea, right? That sensitive dependence as you reach the critical point, right? Okay, so essentially, you all know what a magnet looks like, right? At large scales, this is a piece of iron that's been magnetized by the Earth's magnetic field, essentially. So it'll have a north pole and a south pole. The way that we model such magnets is actually, if you were to zoom in like that, you can imagine that this is actually containing lots of microscopic magnets. So they're actually spins, but that's not really important. They behave in exactly the same way as tiny magnets. So you can imagine that basically what's happening is that if this is fully magnetized, so fully magnetized means that you're here, for instance. So fully magnetized state just means that all the tiny magnets, the microscopic magnets, all point in the same direction, or rather almost in the same direction, right? Because this, in any kind of material, there'll always be some kind of random motion, right? Because this has a finite temperature, right? So you can imagine that each of these tiny magnets is sort of like moving around a little bit, but they're all broadly aligned. On average, they're all oriented south to north, which means that if you take the average over the entire constituents of the magnets, then you get one big magnetic dipole, as it's known. Okay, so this is the fully magnetized state. On the other hand, when you've heated this thing way beyond its critical point, way beyond its Curie temperature, as you heat it, well, what's going to happen is you can imagine that when you heat things up, they tend to move around randomly. And basically, when everything starts moving around randomly, then the sort of like stable configuration of the system is just going to be, a system that maximizes randomness, right? It's something that's known as entropy in physics. But basically, when it's demagnetized, it'll just look like this. So you'll have things pointing in completely different directions. This. And on average, you have zero magnetization. So here, in this case, your magnet no longer works, right? This was the case, once you heated it, it was no longer, this ferrous bit of metal is no longer attracted to the magnet here because it's actually lost its own magnetic properties, right? So the question is, what happens in between, right? Because it's fairly easy to understand what happens here, it's fairly easy to understand what's happening here, because, random motion just means that despite the fact that the tiny magnets here, they want to be aligned, but the temperature keeps rejiggling them in such a way that overall there's no alignment of the microscopic magnets. So that's demagnetized, this is fully magnetized. The point of real interest, the point in which something very interesting happens, is precisely here, right? Which is, as you recall, this was the bifurcation, right? So I'm going to rewrite this thing, but with temperature decreasing this way, so that it looks more like the bifurcations we're used to. So this is M, the magnetization, and what happens is that at first, at high temperatures, there's no magnetization at all, and then it diverges, it goes like that. And here, we can start seeing things that are interesting, right? Because ultimately, why does, when you go from this state to this state, right? From the demagnetized to the fully magnetized state, why does it pick a direction? how does the magnet know to align its north pole here and south pole here and not just flip it the other way around, right? Well, the answer is obviously the system doesn't know, right? What the system does in this case, right, is that it's going to, all of these things are going to align in this direction because there's another magnetic field present. In the same way, this is basically how magnets form in the Earth's crust, right? In the Earth's crust, you have, a whole bunch of ferrous metals which have magnetic properties. At the start, they're very hot, they're demagnetized, but eventually they're going to settle into the magnetized state, and what's going to determine the direction of their magnetization is just the Earth's magnetic field, right? It's the Earth's magnetic field that's going to determine that you're going to go on this branch, and not, for instance, on the other equally probable branch, which is this one. So this is why, when we saw dynamical systems, we saw both branches of the bifurcation, right? Whereas actually, in a magnetic system, we only ever see one of the branches. But you only ever see one of the branches because the system, at this point, at the critical point, the system was forced to pick a direction, right? And so this is basically what you observe with the Curie temperature, right? But what we want to know is, okay, so what's happening here? Because at this point, at the point of the bifurcation, the magnet is basically free to choose, right? It can go up or down. It can choose to align itself north-south or south-north. Ultimately, in a real system, what will determine what branch you go onto is the surrounding magnetic field. But imagine this magnet was completely isolated from any outside influence. Then really, there would be no way to tell, right? It would really be a 50% chance of going here and a 50% chance of going here. And we can try and understand why that's the case, right? Because basically there's a property here at the critical point where you have very large magnetic susceptibility. And I'm going to explain what this means. So essentially, once you've reached the critical point, any tiny nudge will determine the orientation of the whole system. Because what's happening here is that as you reach the critical point, all of these magnets, tiny magnets, they're still disordered. But they're now at a point where any small fluctuation, so for instance, you're in the demagnetized state like that, but suddenly two magnets start to align. And they align in this direction, just by random fluctuations. So this means that in this case, the entire magnet is going to align in this direction. But now imagine a different case. So still, random fluctuations here, but this time two of the magnets have aligned in a different direction, in the south direction. And basically this means that this creates a tiny magnetic field, and this tiny magnetic field aligns the entire system with it. So this is basically the reason for critical behavior, right? All of this is critical behavior. If any of you have ever done some ancient Greek, critical is from the Greek krinein, which means to choose. It means a fork in the road, basically. And this is why it's a critical point, right? Is because once you reach this very specific point, your system is going to be extremely sensitive to any kind of outside influence, because precisely at this point, it doesn't know whether it should go on this branch or whether it should go on this branch. So what's going to happen is that if a few of the magnets within the system start to align in one direction, and they will do so randomly, right? Just because temperature fluctuates the directions of all the magnets. Well, if a few of these align randomly, then that small fluctuation is going to have the effect of pushing the whole system on this branch or on this branch. So this is basically the kind of sort of like deep physics behind these critical phenomena, right? Is that suddenly you have a system that is incredibly sensitive to tiny microscopic changes, right? So you can imagine as a political metaphor, right? This is these few magnets aligning randomly, they're the right people at the right time, and suddenly your entire system becomes modified simply because your system was unstable to begin with. So it takes very little to drive it in one direction or the other. But the interesting thing is that in the case of the physical systems, well, there's no reason initially to assume that it'll go in this direction or this direction. It really is a toss-up, right? So that's something that is unusual for a large physical system, right? Because as you recall, large physical systems, so such as the air in this room, you only really care about their average properties, right? You care about the temperature, the pressure, etc. So you shouldn't care about what's happening on the micro scale, really. That should be irrelevant, right? If two molecules in this room start behaving weirdly, like, no one cares, right? It's not going to change anything. But when the system becomes critical, actually it will matter, right? These two random magnets that have aligned in one direction, they will actually have the effect of taking the entire system with them, right? And this is, again, unusual in physics in that usually we either think of studying microscopic stuff in detail or macroscopic stuff as average properties. In this case, you really can't afford to do this, right? Nothing about the average behavior here will give you any useful information. It really is the micro scale that will determine what will happen at larger scales, right? So that's a kind of, that's the sort of like crux of critical phenomena, and you can start seeing what that has to do with, so near the critical point you have the susceptibility, which means the ability of magnets to align, which becomes very, very large, and so any small deviation will suddenly align the whole system with it. Okay. So the critical behavior is what happens precisely at that point. So what happens is initially your system, so your magnet, is composed of a lot of tiny magnets which are all randomly misaligned with each other, right? And they're all moving around because of temperature, right? Any system with non-zero temperature, everything's just like wiggling around a little bit, right? So in this case, in the case where it's demagnetized, it all wiggles in random directions, and all the tiny magnets kind of cancel each other's effects out, right? So here, this is not magnetized. But what happens is, as you reach this point, what happens is the susceptibility of the system becomes very large, meaning that your system is now very sensitive to any kind of small change. Now, this should ring a bell, right, actually. This idea of like being very sensitive to small differences. Because this is the whole point of chaotic systems, right? Chaotic systems are systems that display sensitive dependence on initial conditions. And you remember as well, maybe, why they displayed such sensitivity to initial conditions. It was because at some point, if you were looking at the evolution of the system, if this is the potential energy, for instance, as a function of position, then you remember what was happening in nonlinear systems was that you started having one of the fixed points that became unstable. So this is unstable. This is an unstable fixed point. And as you recall, in an unstable fixed point, any small perturbation will get amplified. So this is positive feedback here. So you can think actually of this critical temperature as the system being in this state, right? It's at this unstable fixed point, and suddenly any tiny change will nudge it either left or right. But the point is, once it's chosen, it's not coming back, right? Because any small deviation, it'll choose this well, it'll fall into this well, or it'll fall into this well. But once it's there, it can't climb back, right? No small perturbation will allow you to climb all the way back up again. So this is something which is a very generic feature of chaotic systems, right? Is that at some point they have some stable fixed points and an unstable fixed point in between. And that essentially this is the thing that will drive the sensitive dependence on initial conditions. And actually, if you were looking at a magnetic system, you could draw a very similar plot to this one, where instead of the potential energy of a spring, it'll just be the potential energy linked to the magnetic energy, basically. Okay. So, what we've been saying is that, so this is the bit that I was describing in the introduction, right? So that ultimately in physics we usually see only microscopic or only macroscopic, but actually with phenomena like turbulence and phase transitions, the microscopic manifests as dramatic behavior on large scales. And we can already see as I've explained here, the link between these systems and chaotic systems, right? The key thing here is positive feedback, right? As your system reaches an unstable fixed point, it becomes very susceptible to small changes. But the reason that it doesn't just grow, the reason that it doesn't just move away to infinity, right? The reason that ultimately your system doesn't completely break down as it moves across the unstable fixed point is that the unstable fixed point is not alone, right? Because of the nonlinearity of the system, you have stable fixed points on every side, right? Which means that eventually there is a bound to what the system can do, right? In the case of the magnet, it's very simple to see, right? So at some point, at this point, the system is unstable, so any small change will drive all the magnets to align, but once all the magnets are aligned, the system is stable, it's here. So nothing changes anymore, right? And you had the same thing with, the Duffing oscillator, for instance. So it was just an oscillator where it has an unstable fixed point and two stable fixed points here. And the presence of the unstable point meant that the motion was chaotic, right? But still, the oscillator doesn't go away to infinity, right? The presence of positive feedback at some point gets counteracted when you go back to the region of negative feedback here. And this is a key point, right? Just because you have sensitive dependence on initial conditions doesn't mean that that the difference between states will grow infinitely. To take a very simple example, right? So I told you very early in this course that weather forecasting is a chaotic game, right? Because very tiny differences in local pressure gradients or temperature gradients, these will have dramatic effects on your forecast. So the way to imagine this was with the exponential growth in the pandemic, right? You missed out 3 patients on day 1, and suddenly your error for day 10 is like in the thousands, right? Well, the thing is, that can't happen forever, right? At some point, you will never be wrong in a weather forecast by more than 100 degrees, right? However sensitive to initial conditions your system is, like, even, you're not actually, your weather forecast is going to be correct within your plus or minus 20 degrees if you're very bad at it, right? So this is something that really that's a kind of like additional layer in chaotic systems, right? You have on the one hand the destabilizing factor, this highly sensitive dependence on initial conditions, but at some point this all needs to be folded back in, right? Because you can't have, for instance, the uncertainty on future temperature. That uncertainty can't increase forever. At some point it has to fold back in, and the uncertainty will never grow beyond a few degrees, maybe a few tens of degrees if you're very pessimistic. Okay, so this is a sort of, slightly wishy-washy way of trying to introduce this idea, but really, try to imagine this, right? The initially sensitive dependence as things diverging like that, and then at some point they can't keep diverging. They have to fold back somehow, right? And this idea is that you're stretching the uncertainty, then it has to fold back in, and eventually it'll form a very complicated topological structure, which is actually what we'll see as the main, the sort of like main event of this thing, which is the strange attractor. So this is something that the sort of like take home here, right, is that the phase space structure of such a system, it has to both have boundedness, because it can't explore, your oscillator is never going to be kilometers away from its equilibrium position, so it has to be bounded, but it also has to be infinitely complex, right? Because with the Duffing oscillator, for instance, it became chaotic, and when it's chaotic, it never repeats itself exactly, right? So this is something very important, right? So basically the question becomes, how do you fit this kind of infinitely complex trajectories which never cross, how do you fit this into a bounded space, right? And we'll see that the answer is fractals, but I'm getting ahead of myself a little bit. Okay, so first, a kind of like back to basics thing. Because I did introduce the notion of phase space, but I think it's it might be a bit stale now. And it really is the key thing to understand for this lecture. Okay, so the initial system that we're going to present, it's one that we've seen before a great many times, right? It's just a simple harmonic oscillator with extra damping. So what you can imagine is that, the little mass here is tied to a spring, oscillates around, but it's also got some friction force. So it's not going to oscillate forever. You remember, if you were to plot this in time, so if the y-axis here represents the amplitude of oscillations, and this is time, then what this thing is going to do is going to start out like this, and then decrease like that, right? So this is something that describes, damped oscillations. We go like that. One of the interesting representations of such a phenomenon is in phase space, right? Instead of just describing how, well, actually I'm going to call it x. Instead of just describing how the displacement changes over time, I want to see the trajectory of my system in a space that has velocity on the y-axis and displacement on the x-axis. Like this. So this is displacement, this is velocity. You remember for the simple harmonic oscillator, so I'm going to draw it just in dashed lines. So this was the simple harmonic oscillator, it just circles around, right? So if you start out here, you're just going to move in cycles, right? Which is very simple to explain physically, right? Initially, you're far from the equilibrium position of the spring is taut, you have a large potential energy. This potential energy gets converted into kinetic energy as you move towards the equilibrium position. Then here, you've reached the equilibrium position, you're now moving away from it, so your spring is now working against you, you're slowing down, and you reach the opposite, you reach the symmetrical point over here. So this is simple harmonic motion, this is no damping. And what happens is that in this ideal case, your system just circles around in phase space forever. Obviously, we're not here in this particular case. Here we've introduced damping, which means that as the speed increases, friction is going to remove energy from your system, right? So your system loses energy, so instead of going in circles, it's now going to go into a spiral, like that. And eventually it'll just reach this point here. So this point here, the origin, O. O is what's known as a point attractor. What does this mean? It means that ultimately, any trajectory that starts out around here will eventually come to the attractor. So I'm trying to see, I seem to have no longer have a blue pencil, that's fine. I'll just do another black one and we'll do for this one dotted lines. So in the dotted case, you get something like that. Tuk, tuk, tuk. Okay. So as you can see, it will circle back to the origin. But here something interesting is happening, right? If you were to look, instead of just the lines, let's look at the way that the phase space, so the area, a patch here, let's see how it behaves as it goes through the orbit, right? Well, you can see that if you have a patch here, as it evolves, it's going to become smaller and smaller. So this patch, the difference between two neighboring orbits, this patch, it becomes squeezed as you go towards the attractor. And this behavior, this is something that's characteristic of dissipation, right? It means that two neighboring trajectories, they'll come closer and closer until they reach the attractor. So you can imagine the difference getting squeezed as you circle round. We can also actually ask ourselves, okay, so this is the undriven, the free oscillator, right? So I've just taken my spring, pulled it, dropped it. But in a lot of the systems we were studying, there was a driving force, right? So we can have a look at what happens when you have a driving force. Because here we know that if the system is linear, right? So recall, this system is a linear system, meaning that it responds proportionally to the driving force. So this is something, everything I'm saying here is for a linear system. So this is linear and dissipative. And in this case, these are free oscillations. Now, we stay linear, but this time we have driving. And we kind of know what happens, right? So imagine, if you have a pendulum with a small motor at the tip over there, that motor, drives the pendulum to continue its oscillations. So that pendulum will never die down, right? It will just keep on oscillating, and the amplitude of the response is going to be directly proportional to how much your motor is working, right? So in this case, what's going to happen is that you'll have this kind of behavior. So at first, say you start out over here, at first there's going to be, the transient, so some kind of initial thing going on here, but eventually it's just going to settle into a circle, meaning that, imagine I've got my little pendulum with a kind of motor driving it. I switch it on. At first, there's going to be the transient response. So the pendulum, as I switch on the motor, the pendulum starts oscillating a bit wildly, and then it'll settle into this particular pattern. So this here will be a periodic attractor, right? So this is also an attractor, but this is a cycle. Because essentially, it doesn't really matter where I start out, it will go towards this thing. So this bit here, that's the transient. So this is the transient, and the circle here is just the steady state. So this is something that is possible because my system is linear. Basically, the only thing that really matters in the steady state is how much I'm driving the pendulum with my motor, right? And depending on the resonant frequency of my pendulum, and depending on what frequency I'm trying to drive it at, then the response will be large or small, right? You remember if you can imagine with a swing, right? If you try to push a swing very far from its resonant frequency, the response will be bad, whereas if you push a swing at exactly the right frequency, the response is large. But in both of these cases, the system remains linear, right? In that response is proportional to driving force. It's just that, it'll respond better or worse, depending on the frequency you're trying to drive it at. But nonetheless, there's still a linear relationship, proportionality. Ooh, I've got the R of attractor. Okay, so that's what happens when you drive the system. For a linear system. For a linear system, it will just settle into this steady state behavior eventually. And that steady state behavior, it'll just depend on what frequency you're trying to drive the system at. And if you're driving, you've got a pendulum, if you're driving it with a frequency of 10 hertz, then it will respond, the system will respond at 10 hertz, but it'll respond well or poorly depending on the system's own resonant frequency, right? Really just think of the swing, this is exactly that. So the steady state is really just this cycle here. So as soon, it would have been easier if I still had the blue marker. I'm very much missing it. But this is the steady state, the thing I've kind of double marked here. Meaning the reason it's an attraction, the reason it's a steady state is that once you're on it, you're just going to keep staying on it, right? It no longer moves around, right? The transient here, the response is evolving with time, but once you're on the steady state, you just stay there, right? So at this point, your motion starts looking like a simple harmonic oscillator, right? Okay, so this is what happens when you add driving. Now, let's see what happens when you have an unstable fixed point. So instead of having, instead of oscillating in a potential that looks like a well, like this, so this was the simple harmonic oscillator. So the simple harmonic oscillator, you can imagine you're just moving around here. But this time, we're moving in an unstable potential, meaning we're no longer at the bottom of a well, we're on the top of a hill. If you're on the top of the hill, then obviously any small deviation, you're actually going to move away. And so you can imagine this is kind of like, instead of, if you were to inverse the dynamics of this spiral, right? So you're no longer starting out here, you're starting out near the center. You can imagine that basically, instead now of squeezing, we're stretching. So the little patch here it starts out small and gets stretched, which is why initially close solutions will become further and further apart, right? Because the space between them keeps being stretched by the presence of this instability over there, right? So that's the first element, actually, we'll see of how to describe chaotic systems in phase space. A first phase will just be stretching, but you also know that it can't stretch on forever, right? At some point, these neighboring 2 points, they will have to stay in the vicinity of the equilibrium points, right? An oscillator will never deviate by kilometers from its equilibrium position. So what's going to happen is that you're going to stretch like that. So this is the initial sensitive dependence with 2 initial trajectories going further and further apart. But then after stretching, you're going to fold back. And this is the kind of really the motion of a strange attractor, as we'll see. So this is the idea is that, yeah, the unstable fixed point represents a kind of positive feedback, which will drive the system away from it. So it stretches the phase space around it for an unstable fixed point. On the other hand, a stable fixed point was squeezing the phase space around it. Trajectories tended to become nearer and nearer as they orbited towards it. Okay, so we can now have a look. So what we've seen so far, these are all linear things, right? This is unstable, but it's still linear. Now we can look at what happens with our good friend, the Duffing oscillator. So this one, it's nonlinear, meaning that it's not actually going to respond proportionally to the driving force. So what we can see is that initially it kind of does behave linearly, because initially this term, so this term is the nonlinear term, the x cubed term, all the other ones are linear. So all the nonlinearity is here. This is the driving force, this is damping, this is friction, this is the linear spring term, and this is just the acceleration of the system. So with your oscillator, this time, if you're driving it slowly, then it kind of still behaves like a linear harmonic oscillator. So it's not quite a circle, but it still has a nice cycle limit. It has a nice steady state where the oscillator is just going to move around like that at whatever frequency you're driving it. But the point is that as you increase the driving, what's going to happen is that you're going to start to explore the nonlinear parts of the system, the nonlinear behavior. And what does nonlinear mean? Nonlinear means that the system response is no longer proportional to how much you're driving it. Think of it this way. If you have a pendulum, its frequency, its resonant frequency, so the frequency at which you need to drive it to get maximum response, that frequency doesn't depend on the amplitude of the swings, because the pendulum, as long as it's in the linear phase, in the linear regime, your pendulum, it's going to swing at the same frequency, whatever the amplitude. It's something that Galileo noticed back in the days, right? But the thing is, that's no longer true as the amplitude becomes larger, because a pendulum is actually nonlinear. When it starts going into large amplitudes, then the frequency of its oscillations starts to depend on how much you're driving it, on the amplitude of the oscillations. Meaning that as the driving increases, your system is now responding differently depending on whether it's in the small deviation, the small amplitude swings, or whether it's in the large amplitude swing part. So now, because of this difference in behavior between behavior at small amplitude and behavior at large amplitude, your system now goes through its first period doubling, right? Meaning that you remember, instead of responding simply, wait, I'm going to erase that. So instead of responding neatly like that as a sine wave, it now goes something like that. So this one goes smaller, and it goes back big again. So basically, the repetition of the system is now no longer quite the same. Actually, this is a really crap drawing. I'm just going to show you the slide, I think. It's probably way easier. Right, exactly. This was the linear part. So you have behavior very much like a simple harmonic oscillator. And then, as you start exploring the nonlinear parts, then the swing then depending on, on where in your swing you are, you'll respond well or poorly. And that means that your system now no longer has a simple response. It has, basically, you can imagine it as having two frequencies in its spectrum, no longer just the simple frequency here, but two frequencies, what's known as period doubling, which we saw a while back as well. Okay. There's nothing. Okay. So that thing is still not chaotic, right? It no longer has a very simple behavior, but still not chaotic. But at some point what happens is that your system starts exploring the part of the part of the potential that looks like this. So you remember, this is potential energy of your oscillator as a function of displacement. So in this regime, you're only exploring around here. So this is linear. In this regime, I'm going to make it like that. There we go. In this regime, this is no longer symmetrical, right? Which means that the behavior here is going to be different to the behavior here. So you're now nonlinear. So your system oscillates like that. And then at some point, it's going to cross the unstable fixed point. And instead of staying around here, it's now going to move around from one basin, from one well to the other. And it will do so at some point chaotically, right? And you can see the structure of this thing, actually. This is what we mean by a strange attractor. You can see that ultimately your system remains bounded, right? Its maximum velocity never exceeds around 1. Its maximum displacement never exceeds around 1. But this trajectory is infinitely complex, right? It never repeats itself, and it has this weird structure where if you were to zoom in onto any of these lines, you'd see that there are nearby trajectories everywhere, right? And I think it's probably easier to actually, well, it'll be easier to visualize this as a kind of movie. So if there's a short animation, which I'll show you in a minute. Okay, the take home here is that as driving increases, the system becomes increasingly nonlinear, which means that the resonant frequency of the system, its response to driving, will change with the amplitude of oscillations. This means that you're no longer in the linear regime, your response is no longer proportional to the driving. You go through period doubling. This is this bit. Then at some point, the unstable fixed point comes in. It starts driving the sensitive dependence, right? Because here, there is no sensitive dependence in this bit. In this bit, nearby trajectories remain reasonably close. But as soon as you start feeling the effects of this unstable fixed point here, of this positive feedback that occurs around here, then you start seeing the sensitive dependence. And then the system becomes chaotic. So the system becomes chaotic, but it still has, there are still fixed points in the system. So eventually, if you get kicked out of this basin, you'll just fall into the other basin. And then you'll eventually get kicked out of that one, but you will fall into the other one eventually. Which means that despite the fact that none of this behavior is predictable, the structure of the attractor is predictable, right? You do know that the system is never really going to leave this area, right? And you can also make some educated guesses as to how long it's going to spend in each basin and things like that, right? So chaotic doesn't mean you can't say anything about the system. Chaotic just means that you start saying different things about the system. You can no longer say, what's the position of the oscillator going to be in like an hour? But what you can say is that on average, it's going to spend most of its time around here, and not so much of its time around here, for instance, which is still useful information, right? Okay, so in order to see really what I mean by this kind of like stretching and folding of phase space, the best thing to do is really to just actually see it in, it's actually just, see it as a video. So I'm gonna just, I think, whatever. Okay, so since the Google, there we go. Okay, there we go. I'm going to cut the sound because it's going to be very irritating very quickly. So this is the Lorentz system that we saw earlier. Remember, Lorentz was just the simple model for convection in the atmosphere. So I'm going to skip this bit. because this is stuff we've already seen, and really what we want to see is this part. So what is this? Here, I started out the system in two initially very, very close positions. So there's a yellow ball and a blue ball. They represent where in the phase space you're initially dropping your system. And then what we're going to see is how this thing evolves with time. So this is what you're looking at here is evolution in phase space, right? So evolution in the space of the system variables, not in time. Basically, the evolution in time is the trajectory. So as the ball moves around, it draws the trajectory in phase space. Okay, let's do this. So initially, well, they're close by, they remain close. Already you can see that they're diverging a little bit. And that divergence is just increasing more and more until at some point, well, they don't really start looking alike at all. But if you look at the structure of the thing they're drawing, so this is three-dimensional, right? This is spinning around because the Lorentz system has three variables. Well, it's starting to draw this kind of complicated shape, but you can see there is regularity, right? This isn't random stuff. All of this is deterministic, and there's a structure to this tractor. It's just not something you're used to seeing, because here, none of this behavior ever repeats itself, right? You'll notice that this system, at no point is it settling into a cycle, right? At no point do you just have the regular, circling around in phase space that you would get with a limit cycle. So this is just going to continue forever and ever, but you'll notice that the fact that there is initial, so there's a very strong initial dependence on initial conditions, but that doesn't mean that the trajectories don't come very near each other again and again, So as you can see, here they're near again, now they're going to go back to being separated, and back again here. So this property of nonlinear, of chaotic system is called recurrence, right? And this is another attribute of chaotic systems. So basically, we've seen two so far, right? So the two things we saw so far are that they're deterministic. So this is a kind of definition of mathematical chaos. So it has to be deterministic. So we don't have any random effects here. It has to be nonlinear, because a linear system will always settle to some kind of predictable, repetitive behavior, right? So it can't be linear, but it also has to be recurrent. And what I mean by recurrent is that if you look at the blue and the red trajectory, what you'll notice is that I can always find infinitely close to any blue trajectory another blue trajectory, meaning that the system will always come back arbitrarily close to the point at which it started. So it never repeats itself, it never comes back to the exact same position, but it does eventually come back to an infinitely close patch of the phase space where it started out. So for instance, if we're starting out here, then maybe for a while we'll go on exploring other bits of the attractor, but eventually we will end up just in the neighboring trajectory here. So this is what we mean by recurrent. And recurrence is a thing that guarantees that none of this kind of blows up, right? Our weather forecast is never going to be, 10 degrees off. Because actually, despite the fact that the trajectories never cross, that no behavior is ever repeated, well, they still remain within these bounds. This attractor has a finite volume in phase space in a way. Yeah, wait a sec. I'm just going to freeze this. Yeah.
The fact that it never comes at the point of attractors because the system is non-linear.
So the fact that it never becomes, the fact that it's non-linear will mean that it never comes back, well, the fact that actually that it's sensitive to initial conditions and non-linear will mean that it never comes back to it never comes to a limit cycle. So it never goes around a repetitive loop. The reason that the two trajectories never, what was the question again? I got lost, sidetracked.
These two molecules, they never come back to the point attractor.
No, there is no point attractor here. So this is the thing, this is the attractor. What you're seeing here, this is the attractor. There's no point attractor here. At no point is any of these molecules ever going to reach the center here. There will always be gaps in the middle. So this is the weird thing, actually. This is why, this is why they're called strange attractors, these things. Oh, sorry, I forgot to add that all this means sensitive dependence. Plus boundedness. Yeah, so this is why they're called strange attractors. Because the kind of attractors that we're used to seeing in physics, in linear system, is either a point, meaning, this is the death spiral of our damped oscillator. So here, everything just ends up at a point. That's a simple point attractor. We also saw that there were limit cycles, so circle attractors, which was the case of, for instance, the driven damped oscillator or the undamped oscillator. They eventually reach a circle. But if the nonlinearity of the system is small enough, it'll still settle in, it can still settle in that kind of thing, right? If you remember when we were looking at the Duffing oscillator over here. Right, there we go. So when we were looking at the Duffing oscillator, there was a bit of the space where the nonlinearity was small enough that it still ended up in a limit cycle. It's when the nonlinearity becomes large enough, when this term becomes important, that then you settle on your strange attractor, right? And the reason it's strange is that, yeah, it's not a point, it's not a circle, it really is just this shape, right? It is what it is, right? As it turns out, it has a fractal structure, but yeah, there's no other name for it, right? It's just a strange attractor. It's not a point, it's not a circle, it's not, a figure of 8 or anything. Like, it never really repeats itself, because you could imagine having a kind of attractor which would look a bit like a figure of 8 that does exist, but this is not the case here. Here it really never does repeat itself. There's no, yeah, this is the structure. Okay, and so this is what it looks like, kind of frozen. But you see, I think looking at it in motion gives you a better, I think, intuition for what's going on here. Okay. So here's another attractor. So this is so here that was the Lorentz attractor for the Lorentz system. As it turns out, there are many types of attractors, right? And they all have different shapes, but they have similar features, right? So this is an attractor for a system known as the Hénon system, which is again a fairly simple map as well. But the point of the Hénon attractor is that it actually gives you a very straightforward illustration of why attractors are fractal, right? Okay, so the idea is that here, this is the structure of your attractor in phase space. This is the phase space, these are the state variables. And you can see that here there's the thing that looks like a thick line, right? But the thing is, it's not actually a thick line. If you zoom in, it's actually 3 lines close together. This is important, because look, you zoom in, you have 1, 2, 3 lines. This line looks a bit thick. If you were to zoom in, you would get exactly the same feature. This is not a thick line, this is 3 lines. And you would do this again and again, in the same way that this line is not actually 1 line, it's actually 2 lines. So basically, if you look at this thing, this attractor, so this is if you were to drop a kind of, if you were to start out the system somewhere, then it would always keep moving along this attractor. It would never leave the attractor. But this attractor, seemingly simple, actually has a very complex structure, because everything that looks like a line is actually several lines, right? So that your system is still recurrent, because eventually it will come back very near to its initial starting point, because if you zoom in on these things, you see these lines are all very, very close, but it isn't ever going to repeat itself. This is actually completely new. There's an infinite number of trajectories contained within this thing, because once you think you've exhausted the visible bit here, actually it turns out there's another bit in the thick line, right? Because the thick line has 3 lines, another thick line, etc., and so on to infinity. So I'm showing you the Hénon attractor because this one has its fractal structure is fairly obvious, right? The idea that actually, despite looking simple and being bounded in space, it actually has an infinite number of trajectories that never repeat, that are kind of folded into it, right? Again, like this is kind of there's really a kind of kinetic feeling to it, right? This is what chaotic systems do is they stretch the phase space, they fold it back, they stretch again, they fold it back, until you have this really intricate layering of trajectories in the phase space, which translates as a kind of fractal structure. Okay, so now I'm going to have a little detour about the fractals themselves because they have all kinds of interesting properties. So the first one, this is a classic like fractal question. So this is actually this is the name of a paper by Mandelbrot, one of the founders of the study of fractals. So he asked a stupid question. He said, "What's the length of the coast of Britain?" Well, the idea is you just measure it, right? So this is one way of measuring it. You have, a yardstick, and you walk the coast of Britain with your yardstick. And once you've gone round, you say, okay, it measures, I don't know, a few thousand kilometers. I've actually no idea what the real value is. Okay, but you're a geometer, you're a man of precision, and you say, well, my yardstick's too big. So you shrink the yardstick, and you do it again. You walk the coast of Britain with your shorter yardstick. Now, you notice the larger yardsticks, they miss a bunch of details, right? So actually, the distance between these 2 points, for instance, if you follow the coastline, is actually much larger than your yardstick would assume. So as you decrease the size of your yardstick, well, the length of the coast of Britain increases. And there's a kind of silly question to ask, but how long can you keep doing this, right? You take a smaller yardstick again, you walk the coast of Britain again, your length is going to increase. You do it again, and this is really recurring, right? You do it again and again. And the thing is, in theory, this never settles, right? So the coast of Britain is infinite, at least if you think in mathematical terms, right? Because if you were to assume that the coast of Britain was infinitely detailed, well, in that case, really, every time you picked up a smaller yardstick, you'd just discover finer details, and you'd never settle to a given value. And this is something you can actually observe. So it has a name, it's called the coastline paradox. And you can see it here. So this is, again, a little animation of what happens as you decrease the yardstick. So over here, that's the scale of your yardstick, and this is the length of the coast of Britain. And it just keeps going up. Like, it really is never going to settle. Now, in reality, no one's measuring the coast of Britain to the precision of a grain of sand, right? So obviously, in some real sense, the coast of Britain isn't infinite, right? But in mathematical sense, if you think of the coast of Britain as having this kind of like infinitely detailed structure, then it really has an infinite length. So this is an example of fractal properties, because it's kind of like the strange attractor. It has infinite detail, an infinite length, but it's actually contained within a finite area, right? There's nothing, I can draw a square around here, and none of the points would come out, of these points would come outside. Still, this thing has infinite length because of its fractal structure.
But that's practically not true then.
Pardon?
It's practically not true.
Well, it's practically not true simply because you, the person measuring the coast of Britain, you never use a yardstick that's the size of, a centimeter or a hair or whatever. So eventually, eventually reasonable people come to an agreement and they say, we don't care that this rock increases the size of the coast by, 1 meter. Like, we're just going to take maybe we'll take a 2 meter or 10 meter yardstick and that'll be it, right? But that's actually a fairly deep question, right? Because in physical systems, there is always what's known as a cutoff, right? In that actually, there is a length scale below which there's no meaning, right? There is length scale, once you reach the size of atoms, then the question of, whether you can take a yardstick that's smaller than an atom becomes, it becomes meaningless, right? So we know that in real systems, they're never perfectly fractal. There's always some kind of cutoff at some point. Because this thing, which is known as self-similarity, right? The idea that as you zoom in, you get finer and finer details, right? And that this structure keeps repeating on smaller and smaller scales. Self-similarity in reality always has a cutoff. At some point, things stop looking the same. At some point, you reach a wall, right? And you can't actually make your yardstick smaller than an atom. So that's an interesting lesson because actually this is something you might have noticed in very old films. The way that you want to model a ship in a storm, right? If you have very old school, cheap special effects, then what you do is you take a large basin of water and you wave it around and you have a model ship going around on your basin of water. Now that looks kind of real because actually you have a sort of self-similarity in the physics of it, right? In that the physics of a big water basin are roughly the same as the physics of, say, an ocean. But it's not quite the case, right? Because basically, in the ocean, the cutoff scales are much larger than in your water basin. In your water basin, the cutoff will be determined by the size of the basin itself. So you'll always notice some slightly weird things in these old films because the water doesn't behave exactly the way it should, right? Because you're using a different cutoff length for the self-similarity. Okay, so this is the coastline paradox, which is actually, again, very famous article by Benoit Mandelbrot, who was a funny figure himself. Actually, at some point, maybe I'll spend, maybe on Friday, I'll spend half an hour kind of introducing you to the panel of characters that made chaos theory, because they're very weird, most of them. Okay, so fractals, you see them quite often in nature, right? In particular, you see them, this is a kind of very famous example, right? This is Romanesco cabbage, or Romanesco broccoli, I think it's called in English. Anyway, it's a brassica. So, this is obviously very pretty, but there's a question of, why is it that in nature, quite often, when you see very, very complicated structures, at least complicated looking structures, they tend to have fractal structure, right? Snowflakes are kind of the same, right? Snowflakes also display a kind of fractal structure. And there's a kind of a simple answer as to why, right? Is that ultimately, the amount of information contained within the Romanesco cabbage's DNA is finite, right? It doesn't actually have an instruction plan for an infinitely complicated cabbage shape. But what it does have are simple instructions for a process, right? It says, grow a tip. As you reach the edges of the tip, grow other tips. As you reach the edges of those tips, grow other tips. And you have this kind of, fractal thing going on. So this is one of the ways, actually, in which fractals relate to chaos, right? Because we kind of lost chaos for a few minutes there, but we're back to it, right? Because ultimately, why is it that you often find fractal structures in chaotic systems? Is because chaotic systems are deterministic, and the dynamics that govern them, the dynamical equations, they're simple, right? The dynamics are simple. Remember, the Lorentz map, the Lorentz system was 3 differential equations. The logistic map was 1, xn plus 1 equals rxn 1 minus xn, right? One tiny equation. And most of the stuff that you're looking at here, the inner map is also a very simple map, which contains basically 2 variables. So all of these things, they're very simple instructions, but they lead to very complicated structures. And it's kind of the same thing with fractals, right? Fractals also have this, this broad characteristic of being able to generate infinitely complicated shapes based on a set of very simple, repeatable instructions, right? And obviously, there's a sense in which nature is going to work like that because, again, DNA contains a finite amount of information, but you want a shape that's as intricate as possible. Incidentally, there's a question of why is it that fractal structures are so prevalent in nature? So this is an artificial fractal, right? Obviously, this is called a Menger sponge. So the Menger sponge, just looking at it, you can see how it's built, right? Make a cube, dig 4 cubic holes on the central face of each cube, then take each of the subcubes here, do the same thing. Repeat, 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 repeat. Eventually, so the structure that you end up with is called a Menger sponge, and it has a funny property. If I were to ask you what is the volume of this thing? Any guesses as to the volume of this Menger sponge? So the answer is 0. It doesn't have any volume. There's actually, there's no, this thing does not at any point enclose any finite volume. There is no volume here. What it does have, however, is infinite area. Because as this thing, it's again the coastline problem, right? Except this time it's in 3 dimensions instead of 2. But the idea is that your Menger sponge is contained, you can draw a finite volume around here, but the sponge itself doesn't really have any volume. The sponge itself is just a series of more and more intricate surfaces that are textured. As you zoom in to every one of these things, you'll see smaller and smaller holes in the sponge. So, infinite area and a finite volume, right? Why is this a structure that's very interesting for if you're a biologist, for instance, is that ultimately, that's kind of what your lungs are like, right? Obviously not infinite, but basically, it's you probably all heard in high school that if you were to, splatter your lungs in a kind of like flat way. It would cover like the surface of a tennis court or something. I don't remember what the, but your lungs obviously occupy a very small volume, right? And the reason they can, the reason they can actually have such a large surface area enclosed in a few liters of space is because they have this structure which isn't, it's not cubic, right? Your lungs just have like little sacs, and within those sacs, smaller sacs, and within those sacs, smaller sacs again, right? I think they're called alveolars, something like that. Okay. Okay, so basically, this idea that you can contain a very large area within a finite volume is obviously something that's very useful for in nature, right? And natural systems will do this very often, right? Whenever you want to maximize surface area, for instance, you'll end up adopting some kind of fractal structure. Obviously, in your lungs, you want to maximize surface area to have better contact between your blood and the air. Okay. So there's another question. So we've seen in biological systems these fractal structures, what they do. There's another funny illustration, which is actually, so this is another one of Mandelbrot's weird questions, right? So he started out with what's the coastline of Britain, what's the length of the coastline of Britain, and he moved on to another seemingly absurd problem, which was what's the average price of cotton. So he tried to figure out, looking at fluctuations in cotton prices for literally centuries, I think, and he tried to figure out what the average price of cotton was. And he found out that actually there's no actually very compelling answer. There isn't an answer which would not be misleading, basically. Why? Because usually when you think of an average, you think of this distribution, right? So this is what's known as the normal distribution, bell-shaped curve, Gaussian, has many names. And this Gaussian is what happens if you have a random process, right? If you have a random process centered around one expectation value. So for instance, if you imagine I'm not very good at basketball, right? So I try to throw balls into a basket. I'm aiming more or less accurately in that most of my balls will fall around the basket, but a lot of them will just kind of fall to the side, right? But the idea is that if I'm an accurate thrower, meaning that I do know what direction I should be throwing, I'm just not very precise, then the distribution of the positions of the ball around the basket are going to take on this Gaussian distribution, this normal distribution. And this thing's very convenient, because actually I only need to tell you two numbers about this curve in order for you to make reasonable predictions and guesses, right? What I need to give you is A, the average, whether on average I'm hitting the basket, or whether I'm actually so bad at basketball that on average I'm hitting the referee. And the second thing you need to know in order to gauge my reliability as a ball thrower is, well, what's the width of this distribution? This thing called standard deviation, right? So the idea is that I tell you on average I hit around the basket, and the standard deviation is like 2 meters. What does this mean? This means that around 60% of the throws I throw are going to be within that 2 meter radius, right? Around 26% of the throws will be twice that, right? They'll be in the 12 meter radius, and et cetera, et cetera. So the idea is that in a process that is random and that is centered around an average, as soon as I've given you average and standard deviation, really, you're going to be able to make very educated guesses as to how many balls I'm going to put in the basket, as to whether or not, as to what's the likelihood of me throwing a throw so bad that it ends up 20 meters away from the basket, right? You can assign very reasonable probabilities to such a process, right? But the problem is that this only works for linear processes. It only works for certain types of stochastic processes, right? As it turns out, if any kind of evolution follows a more complicated nonlinear dynamics, in particular if it shows self-similarity, and cotton prices, as shown by Mandelbrot, do display self-similarity, meaning that if you were, so this is obviously going to be a completely random drawing, right? But if P is the price of cotton and T is the time, then it'll look something like that, right? There's a kind of like fluctuations. And the idea is that what Mandelbrot figured out was that if you zoomed in on any part of the history, you ended up having similar fluctuations, right? Meaning that if you rescale the problem, well, the fluctuations on a weekly basis start to look like the fluctuations on a daily basis or on a yearly basis, just on a different scale. So this property of scaling, of self-similarity, is actually something that he observed in cotton prices. The problem is that if you have scaling, if you have self-similarity, it means that your system actually doesn't have this normal distribution. It doesn't obey linear dynamics. It clearly has something nonlinear going on, which means, concretely, so this is an excerpt from a very short article that I found on markets and fractals. So these are two of the points that they raise. First of all, self-similarity exists in financial markets. So there is a similarity in structure between intraday fluctuations and weekly fluctuations, for instance. And the other thing, this is really the point that is of interest to policymakers and to people actually investing their money into these funds, right? If you were to bet on the future price of cotton, for instance, is that actually, if you were to take this normal distribution, you would wildly underestimate the likelihood of large fluctuations, because your guess as to the likelihood of large fluctuations is based on a model that is linear and is based on this Gaussian distribution. If your error shape, if your uncertainty doesn't follow this normal distribution because there's non-linearity, because there's self-similarity in the fluctuation of prices, this no longer works. And what you're likely to do is catastrophically underestimate how likely it is that you'll have an extreme cotton price fluctuation, which will actually ruin you, right? So this is a kind of a thing that you remember. I was telling you about that in the context of chaos of sensitive dependence on initial conditions, right? It's like nowadays, if you want to make a weather forecast, it's a better bet because of nonlinearity and because your weather forecast won't settle around an average. It's a better bet to just do loads of weather forecasts and see what kind of behaviors you might expect, rather than try and doing one very neat weather forecast, knowing that sensitive dependence will just probably mean that it's not actually accurate beyond a few days, right? So this is a kind of, this is something actually, one of the topics that if you want to explore at a further date, we could. So I'm not a statistician, right? This is not my specialty, but I'd be happy to go on a little journey of discovery with you, and explore sort of the idea of how it is that chaos and sensitive dependence affects different predictive models. So this can be predictive models in the weather, predictive models for financial prices, all kinds of things. Also, again, obviously, I know nothing about finance. Just, that Mandel wrote about cotton. Okay. So, to sum up, we're reaching the end, and I think this is a good point to sort of wrap it up. So in a dissipative system, what we saw is that chaos is characterized by the presence of these structures called strange attractors. Strange attractors have two features, right? They're infinitely complex. No orbit ever comes to a limit cycle. No orbit ever falls onto a point. But they're contained within a finite space. And the reason that they're contained within a finite space is this idea of stretching, folding of the phase space. Meaning that the system displays two important aspects of chaos. It's both sensitive to initial conditions, meaning the two initial orbits, as you saw with the animation, they diverge, they don't stay near one another, but they don't infinitely move away from one another. At some point, they will come arbitrarily close to one another again. And this is what's called recurrence, right? So the idea that if I follow the trajectory of one particle, it never repeats itself, but it will come arbitrarily close eventually to any given point of its trajectory. So this means this thing of both being bounded and being infinitely complex, that attractors will often have this fractal structure, right? As we saw very neatly with the Inon attractor. And this means that that they have self-similarity, so you get features, statistical features amongst other things, that will be the same at every scale, right? Again, think of fluctuating cotton prices, you zoom in, and it's like the width of the fluctuations will be the same, scaled up or down at for every kind of time scale you can look at. So this is also going back to our initial our initial problem, right? Which was, how does this, how do we link the study of chaos to this fundamental problem in physics and in modeling in general, right? Of linking the complicated small-scale dynamics to the larger dynamics. And what we saw is that if we're only interested in systems that are reasonably simple, gas in a room, for instance, then we can just take averages, right? Ultimately, it doesn't matter what the system is doing at a small scale. But we saw that with nonlinear systems, as with critical phenomena, there comes a point where actually the finer details, the microscopic details of your dynamics start to matter, right? Suddenly, the fact that at the root your water molecules are turbulent, your water molecules are moving around, that manifests itself as the flow going from neat and laminar to being turbulent with all kinds of swells and whirls. And this has to do with scaling, right? If you remember the example with the magnet, the idea is that a big magnet is lots of smaller magnets, and and that at the critical point, any tiny change will have repercussions because it'll manifest as a change on larger and larger scales, right? So this idea of scaling is quite important, right? Which is also, you can link it back with the Feigenbaum number as well, right? This idea that very different systems obey the same kind of like scaling laws, where, if you remember the length between different bifurcations, that ratio was always constant. Okay, so this is, I think the main thing here today was this idea of the strange attractor, right? This idea of like this infinitely complex structure contained within a finite space, which really captures the basics of what a nonlinear, a chaotic system behaves like. Tomorrow what we'll do is we'll study chaos in what are known as Hamiltonian systems. So this is kind of like, this is the stuff I'm most familiar with, because this is what applies to astronomical systems. So for instance, stars don't have friction, so we'll see that they don't have strange attractors, they have different things, which is also a question for you to ponder, if you can think of why a Hamiltonian system should never display strange attractors. We'll apply this to astronomy, planets, galaxies, are they chaotic? And we'll also be able to talk a little bit about this initial question I asked in the first lecture, which is the solar system stable? Very old 19th century question with some interesting 21st century answers. Okay, well, thanks a lot for your attention. Again, the reading for this time is just the 3 basic books. And if you have, do you have any questions for what we covered so far? Wonderful. Oh. There it is. Wait, sorry, is this my bottle as well? Yes.
When discussed this one point, which you have to do as very last
Very well, last what, pardon?
I think maybe, I'm not sure, the point was very last susceptibility.
Oh, magnetic susceptibility.
Yeah, when the applications actually start.
Right, this was on this thing, yeah.
Maybe it's technically magnetized.
Yeah.
So at that point, how long does the system maintain itself at that particular point if the temperature does not change at all?
Good question. Actually, that's sort of, this is another one of the differences between reality and the models, right? Is that in reality, you will always have some kind of external magnetic field that will force the system to pick one of the states, right? It's not actually going to remain unstable for very long. If you're on Earth, for instance, well, obviously, your magnet is just going to align with the Earth's magnetic field, right? But this is an interesting question, right? Because this is fundamentally the difference between the mathematical model, which has this perfect critical point, and reality, where you can never really isolate this behavior completely, right? Will always be susceptible to noise and outside influences. Yeah, sure.
When you talk about period doubling, I mean, this is a very big question, but I just want to know at what point in the period doubling process do we actually start seeing chaos?
So the answer to that is that you start seeing chaos in windows, right? It's exactly the same thing if we go back all the way to, there we go. If we go back all the way to the logistic map. Oops, there we go. Unfreeze this. So chaos starts, for instance, around this value, right? You start seeing chaos. So this is after the 3rd or 4th, so 1, 2, 3, 4. This is at the 4th period doubling, you start seeing chaos. But the point is that in any chaotic system, after the first region of chaos, there are always regions of order. If you look here, there's a gap. That gap is actually a region of periodic behavior. If you look here, there's another gap. There's a big gap here, a period 3 loop. And this one is also, again, periodic behavior. So this is one of the fundamental things about chaos, right? One of the reasons it has this fractal structure embedded in it is that actually most chaotic systems will have this regions of chaos interspersed with regions of order. And then if you look at the, if you zoom in on finer and finer scales, you'll keep seeing that same structure, right? So here that's a large region of order, but there are smaller ones here. And if you were to zoom in on any of these chaotic regions, you would still find that structure, alternating regions of order, regions of chaos. So, but again, in reality, you're never going to observe the very fine regions of order because you don't control your parameter with enough precision, right? There's always the back and forth to be doing in this course every time is, am I talking about my model, which is mathematical, or am I talking about the real physical world where I don't have infinite precision in my parameter tuning and I don't have infinite precision in the initial values, right, of my problem? Yeah?
Is the transient and the steady state one the same?
So actually for chaotic system, so for this system, there's a steady state here. So this is just population settling to one value. These are still steady states, but instead of being steady states where you have one value, you oscillate between two. Once you enter the chaotic region, there's no sense in which there is, when you were here in this parameter regime, you remember what it did, the population is fluctuated and then settles, right? So the fluctuating bit, that's the transient, and the settling to a line, that's the steady state. Over here, the steady state is a period 2 loop, it goes like that. But there was also a transient where basically you end up with something like that. So at first large oscillations, then the oscillations die down, and they keep going at a constant amplitude. So that's transient steady state. The interesting question becomes when you reach the chaotic point. In the chaotic regions, there is no steady state. It's all transient, right? No behavior is ever repeated. Therefore, there's no sense in which your system settles. Remember that was the kind of like the deep question that Lorenz asked about the climate, right? Is there a climate? Can we actually, is there such a thing as a steady state system for the Earth's climate system? And the answer is, well, possibly not.